Trends in the periodic table. The periodic table shows the elements in order of increasing atomic number. The elements are arranged in a way that the properties recur in a regular pattern. There are 18 groups and 7 periods in the periodic table. The columns are called groups and the rows are known as periods. Now let's look at some trends in the periodic table. Metallic character. The metallic character of elements is a measure of how easily atoms lose electrons. This character decreases going from left to right across the periods and increases going from top down the columns. Metallic character is dependent on 2 factors. 1. Effective nuclear charge and 2. Shielding effect. Effective nuclear charge is the pull that the nucleus has on the outermost electrons. When you move across the periods from left to right, the number of protons in the nucleus of the atoms increases. However, elements within the same period have the same number of energy levels. Therefore, an increase in the number of protons in the nucleus of the atoms increases the pull that the nucleus exerts on the outermost electrons, thereby making it more difficult for the atoms to lose electrons. Shielding effect. Shielding effect is the cover that complete shells provide the outer electrons from the pull of the positive nucleus. When you go from top down the groups, you notice that the number of shells increases going from top down. This means that the number of complete filled shells increases as well. So the more completely filled shells you have, the more covering is provided the outer electrons. This decreases effective nuclear charge, which we have defined as the pull that the positive nucleus has on the outermost electrons. This makes it easier for atoms to lose electrons. So let us repeat. Metallic character decreases going from left to right across the periods because effective nuclear charge increases. Metallic character increases going from top down the groups because of increase in shielding effect. So generally, metals are found on the left-hand side and center of the periodic table, while non-metals are found on the right. Atomic radius. Atomic radius is measured as 1/2 the distance between the nuclei of 2 atoms that are covalently bonded together. Let's take, for instance, the hydrogen atom. In a molecule of hydrogen, 2 atoms are bonded together covalently. The distance between the nuclei of the 2 atoms, represented as D in this diagram, divided by 2, will give us the atomic radius of hydrogen atom. Atomic radius gets bigger in these cases. As the size of the atom increases, atomic radius increases with it. So the more completely filled shells an atom has, that means increased shielding, the larger the atom would be, and the larger the atomic radius. This is because effective nuclear charge decreases as shielding effect increases. Atomic radius also increases when you have fewer protons in the nucleus of an atom, but the number of shells do not change. So let's say we're looking at period 3 of the periodic table, where we're going from sodium to argon. All members of period 3 have 3 energy levels. However, the number of protons in the nucleus of the atoms increase going from sodium to argon. Therefore, sodium will have the largest atomic radius in that period. So we can conclude that atomic radius increases from top to bottom of the periodic table and decreases going from left to right across the periods. Melting point. Melting point is the temperature at which a solid substance melts. So this temperature where a solid substance turns to a liquid can be used to identify a substance. So we can measure this in terms of the energy needed to break the cohesive forces holding the particles in the solid substance together. The stronger the cohesive forces, the higher the energy that would be required to overcome them. Metals have stronger bonds holding the particles together. Remember from metallic bonding that the bonding in metals is an electrostatic force holding positive metal ions and mobile electrons together. Nonmetals have weak bonds between the particles. The particles in nonmetals are in form of molecules. Therefore, weak van der Waals forces hold the molecules together. This means that metals will have higher melting points than nonmetals. Let's look at the trend in melting point for group 17 elements. These are the halogens. Going from fluorine to astatine, melting point increases. This is in tandem with the gradation in the physical properties, going from fluorine, which is a gas, to iodine, which is a solid. So, as the size of the molecule increases, the stronger the van der Waals forces holding the particles together. Therefore, melting point increases. For metals, looking at group 1 elements, melting point decreases going from lithium to cesium. And when we look at across the periodic table, using period 3 for example, melting point generally increases, then decreases. You can see that it increases from sodium to aluminum, because the electrostatic force within the particles getting stronger. So aluminum has a stronger metallic bond than sodium. It peaks at silicon. Silicon, being a group 14 element, exhibits the giant molecular property, and then it begins to decrease until it gets to argon. Density. Density is measured as mass per unit volume. Density increases with increasing atomic mass from left to right and top to bottom of the periodic table. So for group 1 element, cesium is denser than rubidium, potassium, sodium, and lithium is the lightest. For group 17 elements, fluorine, being a gas, is the lightest, followed by chlorine, then bromine, and iodine. And across the periods, once again, density rises, falls as we go from sodium to argon. Reactivity. The reactivity of elements depend on how easily the elements can lose or gain electrons. So it measures how vigorous an atom can react with another substance. The most reactive metals, therefore, are at the bottom of the periodic table due to increased shielding and lower effective nuclear charge. The metals at the bottom of the periodic table can easily lose electrons. So looking at cesium, cesium is going to lose electrons more easily as compared to sodium. So cesium is the most reactive member of the metal class. For nonmetals, reactivity increases as you go up the groups, making fluorine the most reactive nonmetal. And this is because effective nuclear charge increases and the atoms can accept electrons more easily. Noble gases generally are unreactive, and that's because they have a complete outermost shell. This makes halogens the most reactive nonmetals. Electron affinity. Electron affinity is the ability of an atom to accept electrons and form negative ions. This is measured as the energy change when gaseous atoms gain electrons. Nonmetals have a higher tendency to gain electrons than metals, and this is because nonmetals need fewer electrons to achieve the octet. Electron affinity, therefore, increases going from left to the right-hand side of the periodic table. So looking at the trend across period 3, electron affinity increases going from sodium to chlorine. Argon has the lowest electron affinity because it is a noble gas. Ionization energy. Ionization energy measures how easily an atom loses electrons. Therefore, we can say that the first ionization energy of an atom is the energy required for the atom in its gaseous state to lose 1 mole of electrons. The lower the energy needed to lose an electron, the more easily an element becomes a cation. Therefore, metals become cations more easily than nonmetals. Metals have fewer electrons in their outer shell and lower effective nuclear charge. Therefore, metals lose electrons more easily. So first ionization increases going from left to right of the periodic table. Atoms with higher shielding will also lose electrons more easily. So going from top down the periodic table, ionization energy decreases. Looking at the trend across group 17, so we have fluorine having the highest first ionization energy and astatine having the lowest. The trend for group 1 elements, lithium has the highest first ionization energy, whereas cesium has the lowest. That agrees with increase in shielding effect, lower ionization energy. The trend across period 3, sodium has the lowest first ionization energy, whereas argon has the highest first ionization energy. Effective nuclear charge increasing from left to right. Therefore, first ionization increases from left to right of the periodic table. Electronegativity. Electronegativity describes the ability of an atom to attract a shared pair of electrons to itself. The attraction is enhanced by increased nuclear attraction on the outermost electrons. This means the nonmetals will have higher electronegativity values compared to metals. Remember, effective nuclear charge increases going from left to right on the periodic table. So, nonmetals are found at the right-hand side. That means the attraction that nonmetals have on outer electrons is stronger. So nonmetals will have higher electronegativity values compared to metals. The most electronegative element is fluorine and the least is cesium. Let's look at the trend. Group 1 elements. Lithium has a value of 0.98, cesium has a value of 0.79. It decreases consistently from lithium to cesium. Group 17 elements, fluorine has a value of 3.98, astatine 2.2. This means that increased shielding lowers electronegativity. And across period 3, from sodium to chlorine, in this case, we've not included argon because argon is a noble gas. So, across period 3, from sodium to chlorine, sodium has the least value, whereas chlorine has the highest value. Let us recap. The periodic table shows the elements arranged in order of increasing atomic number. The repeating pattern seen in the periodic table is known as periodicity. Elements in the same group react in similar ways. There's a trend in different properties of elements down the groups and across the periods. Fluorine has the highest electronegativity value, whereas cesium has the lowest. The trends in properties depend on shielding, atomic size, electron pair repulsion, and the pull of the nucleus on the outermost electrons.